Now, just like in single variable calculus, when we integrate a function over an interval, the domain of integration here is a line. It's one-dimensional, and we get out area, which is this two-dimensional quantity. So we integrate a function of one variable, we get this two-dimensional measure. If we look at the double integral over some region of a function of two variables, and this is with respect to whatever those variables are, in this case it's with respect to x and y, we get a three-dimensional quantity. We get the volume under the surface and above the region. Let's maybe look at some examples of this. Let's say we're looking for the volume below x plus 2y plus 3z equals 6, and in the first octet. So if we just schematically get an idea of what this looks like, we've got the x-axis coming out of the board, we've got the y-axis and the z-axis. Now this is a plane whose intercepts, well, if we set y and z equal to 0, we get x equals 6. So it crosses out here at 6. If we set x and z equal to 0, we get y is 3. So we know that our plane passes through those 2 points. And if we set x and y equal to 0, we get z is 2. So that gives us this triangular region up here, and we're looking for everything under that plane in the first octet, where x, y, and z are all positive. So if we go to set this up, if we look at first the shadow of this region in 2 dimensions. So if we sketch out the x and y plane, well, we know that the x-intercept is out at x equals 6, the y-intercept is up at y equals 3, and we've got everything underneath this triangle here. So that tells us that if we go and set up our region of integration now, we see that the x's range from 0 to 6. So if we integrate with respect to x, the x's go from 0 to 6. And then we can integrate with respect to y. And the y values, given an x, the y's run from this bottom curve, which is y equals 0, up to the top curve. Well, that top curve, we have a formula for that. This is in the xy plane, so we know that z equals 0. If we plug z equals 0 into the original function, we get x plus 2y equals 6. So if we now solve that for y, I know that this top line right here is given by 6 minus x over 2. So that's going to be our upper limit of integration. The lowest y value is y equals 0. The highest y value is 6 minus x over 2. And then the function we're integrating is the actual upper surface of this, which is given by what our z formula is. So if we go and solve this for z, we get that this is 6 minus x minus 2y over 3. So this is actually our integrand, the function that we're integrating, 6 minus x minus 2y over 3. So now let's go through and do the integration. First up, we've got to integrate this with respect to y. So our outer integral will just sit, and we'll integrate term by term with respect to y. So first up, that 6, that's a constant as far as y goes, so that picks up a y. X is constant as far as y goes, so that picks up a y. And we integrate here, we use the power rule, we're getting y squared. And this is all over 3. And then we've got to plug in our limits of integration, which are y equals 0 and y equals 6 minus x over 3. And then after we plug those limits in, we'll integrate with respect to x. So plugging in y equals 0, everything zeroes out. So this limit of integration doesn't really mean anything. It's not going to impact the integral. Now we go and plug the upper limit in. And we're going to replace all these y's with 6 minus x over 3. So we've got 6y, which is 6 minus x over 3, minus xy, which again is 6 minus x over 3, minus y squared, 6 minus x over 3 squared. And then this whole thing is being divided by 3, because that was our denominator, and then we'll integrate this with respect to x. Okay, so let's do a little bit of algebra here. First, I'm going to get some of these fractions out of here. So I'm going to factor out the 3 that's in the denominator, along with a 3 that all of these have in common. These actually, I see the common denominator will be 3 squared. So I'm going to factor out 1 over 27, and then that'll leave me inside the integral. Now I've taken care of this 3, I've brought that out of the integral. I've taken this 3 and an additional 3 outside, so that's going to make this an 18. We distribute the 18 through, and we get 18 times 6, which is 108 minus 18x. Now for the next term, we took the 3 that was out of the denominator, we took out this 3 also, and we get a common denominator of 9, so that's going to multiply the inside by 3, so it gives us negative 18x plus 3x squared. And then on this last term, we've taken out the 3 in the denominator and the 3 squared from this denominator, so there are no fractions anymore, no coefficients to worry about. We're just going to FOIL this out. We're going to get negative x squared plus 12x minus 36. And this we can integrate with respect to x. Now this is looking a little better. We can go through, combine like terms, and then integrate. I see we've got a 3x squared minus x squared, looks like 2x squared. And then we've got some x's. I see we've got a negative 18x, which is negative 36x plus 12, will be negative 24x. And then finally we have our constants. We've got the 108 out in front, minus the 36 on the end, gives us a positive 72 dx. And now we can go and integrate this in terms of x. So the 127th will sit there. Now here we integrate term by term. So we've got 2x cubed over 3 minus 12x squared plus 72x. And then we integrate this from x equals 0 to x equals 6. So again, at x equals 0, everything zeroes out, so that limit doesn't contribute to the integral. Now we'll go and plug the x equals 6 in. So we've got that 1 over 27 on the outside. We've got 2/3 of 6 cubed is 216. Minus 12 times 6 squared is 36. Plus 72 times 6. And then you can crunch that out on a calculator, and that'll give you the volume inside our pyramidal region. Along the lines of this, another application of this double integral is the idea of average value. If you look at average value in single variable calculus, we define the average value of a function f on an interval a, b to be the integral of the function divided by the length of the interval. So think of this like the area divided by the base should give you in some sense the average height. So that's the idea here. Now if we take this idea and try to extend it into a third dimension, the average height should be the volume of a region divided by the area of the base. So what that means is that this should be, now volume, as we've seen just a minute ago, this is the double integral over the region of our function divided by the area of the region itself, because the region is our base. That's the shadow of this three-dimensional surface. That's the shadow of it in the xy plane, so that's the area of our base. So this, we're going to define this to be the average value of a function of two variables f. Let's take a look at, take an example of this. Let's suppose we have, we're looking for the average value of f of xy equals, say, xy squared. And we're doing this on the interval, or on, not on the interval, on the region 0, 2 cross 0, 3. Now this notation here means, this is shorthand for saying the x's will range from 0 to 2. So this is our first variable. And the y's will range from 0 to 3. So that's giving us this rectangular region, this box. So to figure out the average value, first, if we look at the area of the region, this region is a rectangle, so the area of the region is 6. If we now look at the volume, that double integral, the double integral over the region of xy squared, well, the x value is going from 0 to 2, the y value from 0 to 3 of xy squared. Now the y value is going from 0 to 3, so my inner integrals with respect to y. The outer integral is that's 0 to 2, and that's my x. Now the limits of integration here are constant, and my function factors up. So I can use the box theorem to rewrite this as the integral from 0 to 2 of x dx times the integral from 0 to 3 of y squared dy. And then these we can evaluate separately. This first one gives us x squared over 2 from x equals 0 to x equals 2. The second one is giving us y cubed over 3 from 0 to 3. This first one, again, if we plug x equals 0 in, that zeroes out, so that won't contribute. We plug x equals 2 in, we get 4 divided by 2 is 2. On the second piece, the same thing happens at 0. We plug in 0 here, that gives us 0. We plug 3 in, 27 divided by 3 is 9. So that says the average value of this function is 18. So we see that in addition to finding area with a double integral, we can find volume as well as average value. So we'll see more applications in subsequent videos.